So everybody, happy to have you here today. And I'm so happy, Charles Bott and Jay Burness, thank you so much for joining us and talking to us about Hampton Roads Sanitation District. And what we wanted to talk about, so a little explanation, Charles, as you know, Charles actually helped us at NAWI last summer when we were scoping out concepts about reuse and direct potable reuse and scales of reuse. And we had a day and a half long workshop in Chicago. And Charles, you were wonderful to attend and work with us on that. And then I heard a version of this presentation, and I thought that it would be really valuable for the NAWI community to appreciate that not only are we doing research, but the most powerful way to do research is to work within an ecosystem of innovation. And really one of the best examples of that around the country is Hampton Roads Sanitation District. So as we get in, I want to start everybody off by doing a few housekeeping items. First of all, this meeting is recorded. And so you'll be able to access recordings after today's event, and they will be available through NAWI's community website. In general, we love hearing your questions. We don't so much love hearing the conversations you're having with your office mates. So if you could mute yourself during the presentation, that would be awesome. And then what we're doing today is we are using the chat feature. So there at the bottom, you can open up the chat feature and questions here. You can ask the questions whenever they come to you, and at the end, we'll go through and answer all those questions. And probably I will unmute you and let you ask Jay and Charles your questions directly. It's inevitable. Some of you have audio issues. All I can say is do what I do and try connecting through your phone. Not much we can do except that, well, it's recorded. So if it really bombs out where you are, you can always watch the game tape. Also, for those of you in the NAWI Alliance, please remember that we get a credit for the hour that you spend with us. So if you go to this website and Smartsheet, you can fill in the hour that you spent with us today, and we can credit that time and as cost share towards the NAWI program. If you are not already following us on LinkedIn, NAWI's LinkedIn site is where we tend to post all of our information and updates, and so that's a great resource for you to avail yourself of. Now, Hampton Roads Sanitation District is in the great state of Virginia, and I think that one of the things a lot of people don't appreciate is that, of course, because our federal water and wastewater regulations and drinking water regulations, because they're pushed down to the states and the states implement sort of the specifics of many regulatory aspects of this federal regulations, each state ends up being a sort of crucible for innovation. And in this case, Virginia is really special. And it's not just because it's the home to Hampton Roads Sanitation District, but also Virginia, as Charles and Jay know, is also doing really interesting things on permitting for rainwater capture, for treatment for direct potable reuse. And it's a very interesting state. And these are two wonderful and very interesting people to join us today. We have Jay Burness, the General Manager and CEO of Hampton Roads Sanitation District. Hampton Roads is big, almost $500 million budget, and Jay is responsible for the large-scale capital improvement programs and has more than 30 years of experience in engineering and financial utility management. Charles Bott, as you all know, is the Chief Technology Officer at Hampton Roads. And Charles, when I was looking at this bio, I noticed your conspicuous dalliance with multiple universities. So this is a sign, friends, when you see utility people who are also actively engaging at the university level, you've got a sign that something special is going on here. Charles has a bachelor's in civil engineering from VMI and master's and PhD in civil and environmental engineering. And with this, I want to actually introduce the true star of today's presentation, which is the Hampton Roads Sanitation District. Many of you know this well, but I think that one of the things that makes Hampton Roads so important, and really Hampton Roads is a national treasure. And it's a national treasure because it's sort of like many things, the confluence of a bunch of circumstances. First of all, it's the 14th largest wastewater utility. It serves almost 2 million residents and multiple cities around Eastern Virginia. But the key thing that really puts Hampton Roads into the special place that it is that it is at the mouth of the Chesapeake Bay, one of the most sensitive estuaries around the United States. And in fact, one of the places in the country where concerns about nutrient management first really drove innovation, both regulatory innovation as well as technological innovation. So because of where they live and because of the role that they play, Hampton Roads ends up being a very important partner for us as we innovate on how to create more sustainable water and wastewater distribution systems. And with that, I invited our guests here for us to learn more about this in not just the utility itself, but Charles and Jay, also the role and the way that innovation and how you build an innovation ecosystem for the utility that you run. So with that, Jay, Charles, thank you so much for joining us here at NAWI, and tell us about Hampton Roads.
Great. Can you see my screen okay?
We can. Perfect.
Awesome. Well, great. Thanks, Peter. What a great intro that was. Again, I can skip all my maps because you already talked about where we are in Eastern Virginia. Again, the 14th, we serve 1.9 million people. What's crazy about our service area, it's 5,000 square miles, about the size of Connecticut. So I'm going to jump right into it. So bottom line up front, we are trying to build this water technology focused ecosystem. Basically, we want to be the Silicon Valley of water technology for the country. And so what we're trying to do is leverage HRSD as an anchor for economic development. And we'll talk a little bit more about that. So these are our objectives. Obviously, we want to advance water technologies. In our minds, we want to be in tech enablers, and we'll talk about the ecosystem concept that we're trying to develop. And one of the things we've always done is we're always researching ways to keep our ratepayer bills low. And so in our culture, it's embedded in us to be innovative. And so Dr. Bott's going to talk about what our current focus areas are: process intensification and decarbonization. And one of the reasons why we are here today is to foster collaboration and knowledge exchange, because we're trying to build partnerships around the country to build out this ecosystem. And at the end of the day, we're trying to create this demand side innovation. And so big picture, this is really an optimization problem. So if you take a step back and you look at our organization and you look at our great assets, you look at we've got one of the largest R&D groups in the country. How can you optimize that to make a larger community impact? So we're a political subdivision of the Commonwealth. We exist to protect public health and the environment, but surely we can do more if we leverage all these assets. And one of the ways we can do that is by driving economic development through this whole ecosystem concept. So these are the four opportunities that we've identified. One, we can incubate or accelerate companies. And so working with, Imagine H2O and Xylem, I had a great meeting with Xylem Labs today. We can attract companies potentially. One of the things, how this idea really came about was last September, Dr. Bott was like, oh yeah, by the way, some folks from Samsung are flying in from South Korea and they're looking at potentially licensing some of our technologies. And I was just like, whoa, wait a second. What if they wanted to build their North American operations? Why wouldn't they build it in Hampton Roads? And so, that really kind of spurred this whole big brainstorming idea. And also, we want to collaborate regionally. So we have our friends from J Labs here on the call today. We'll talk about some of the partnerships we have with them. NASA Langley's in our backyard. Ferguson, $39 billion market cap company. Their global headquarters is in Newport News, Virginia. Dr. Bott's going to talk about some partnerships we have with waste management on a pilot we're working on with them. And then lastly, the idea of industrial symbiosis. Is there an opportunity from circular water economy concepts that we can co-locate an entity right next to our plant? And I'll talk a little bit about that. So here's our big picture concept: idea, test, and invest or mentor these companies. So for us, in our case, the idea could either come from a startup or from HRSD. As you know, we're one of the only utilities in the country that actually collects royalties from the patents and IP that we have. But what's unique about us is our ability to test technologies at scale. So we're not trying to duplicate what Water Tower does or any of those other types of incubators. What's unique about us is our ability, again, to test at scale. And so we're working with 4 startups now. And by testing technologies at scale, we're de-risking those investments. And we're also a reference for those startup companies to help them launch and grow. And so as part of that, as part of this ecosystem, we've got 6 venture capital companies that we're working with, and we also have industry partners that we're working with as well. And so this is a simple term sheet on how we engage with startups. They would pitch to our R&D group, Dr. Bot's group, or whomever, depending on what the technology is. But at the end of the day, there has to be a value proposition. The tech has to show value. The sweet spot for us are startups that aren't starting to sell us stuff. So we get bombarded every day about people trying to sell us stuff. But if they're coming right out of the lab, they're ready to test at scale. If they are willing to do it at low or no cost. The value proposition is we will help them grow. We will be a reference if the technology works. We will provide that test bedding support, get them connections to local universities, connections with the venture capital folks that are part of our ecosystem. And then if it works, we'll provide references to help them scale. And then potentially, maybe if we can help facilitate manufacturing in our region. So here's a great case study of what we're up to. So we're working with 2 ocean alkalinity enhancement startups, Planetary and Crew Carbon. Planetary a few weeks ago just won the $1 million X Prize. Crew Carbon, they've sold millions of dollars of carbon credits already, $5 million in seed funding. And so this is a great case study in the sense that we love this tech so much. We literally just issued an RFP a couple of months ago. We'll be making a decision because the idea is we love it so much, we want to expand that to our other plants as well. And so just think about that. HRSD is going to install this tech at our plants. Other utilities will see that. They can come visit, see that the tech works. We'll have all the data, and we will help those companies scale. So here's the idea about industrial symbiosis. This is one of our plants in Virginia Beach. It's called our Atlantic plant, 54 million gallons a day capacity. Many plants around the country have hundreds of acres around them because this acreage was purchased as buffer around them. And because we're a political subdivision, we're a tax-exempt entity, the city of Virginia Beach receives no revenue for that vacant farmland. We don't receive any revenue for that vacant farmland. So again, from an optimization problem, what is the highest, best use of that land? Could it be a data center that can use that digester gas? This plant averages 40 to 45 million gallons a day. Could they use some of that water to recycle for their cooling? So we just had a meeting this week about potential data center that may co-locate on this property. But again, the whole circular water economy concept, what can we do with our existing assets to leverage them to make a difference in our community? And here's an example. So there's an adjacent military base next to our Atlantic treatment plant. In 2009, they tapped our 66-inch effluent because wastewater is at a relatively stable temperature. They created a heat sink condenser loop system, like a geothermal system at their plant site. And in 2009, they saved $3 million a year, and this is still in operation today. So I'm going to shift gears real quick, talk about our SWIFT program. It's one of the largest water projects of its kind in the world. And bottom line up front for this, we saved our region $5 billion. And like Peter said, in that we are part of the Chesapeake Bay region, but we're not only, that's one huge regulation, but the second big regulation we are dealing with is sanitary sewer overflows. And so had we not collaborated with our region and everybody did their own thing, we would have had to have spent $7.8 billion complying with these 2 regulations. But what we did is we leveraged EPA's integrated plan. EPA's integrated plan framework recognizes that communities don't have unlimited funds to spend on these environmental projects. And so the judge approved our plan in February of 2022. And basically our SWIFT project, the Sustainable Water Initiative for Tomorrow, has dual compliance benefits. And we can do this for $2.8 billion. And so that saved the region $5 billion. So this is probably one of the best examples of the country of not just integrated planning, but using one water for your community, one water concepts. So this is what SWIFT is. Currently, we take our highly treated wastewater effluent, discharge it into the bay or into the ocean. And the idea is dropping an advanced water treatment plant adjacent to an existing wastewater plant, pumping that water that's taken to drinking water quality standards into our aquifer, and it creates a sustainable groundwater supply. It also reduces the nutrients going into the bay. And then I'll talk a little bit about how we could potentially reduce or stop or slow the rate of land subsidence. and then also protect groundwater from saltwater intrusion. Probably one of the main reasons that Orange County has been doing this since the 1970s is to protect their aquifer from saltwater intrusion. So this is an amazing map that some folks from Australia put together. I put in, and I'll put it in the chat later, a link to this map, but basically it shows where all the global purified recycled water locations are, and they're color coded, whether they're just exploring, planned, or in construction, or operating available. Even talks about the type. So like we're doing groundwater augmentation. So this is a great map. Depending, I know there's a lot of water reuse folks on the call to use for the public that's not familiar with water reuse, that may not know that, yes, this is going on not just around the country, but around the world. So in terms of the nutrients, just to quantify the difference that we're making on the nutrient side, if you compare 2021 to 2028, we are reducing total nitrogen by over 70%, and we're reducing by total phosphorus by over 50% with this project. And we have unsustainable aquifer withdrawals. And so if you look at the graphic on the right, in Eastern Virginia, we have an aquifer called the Potomac aquifer. It's a confined aquifer. Basically, it does not get naturally replenished. We've got two paper mills that have been withdrawing tens of millions of gallons a day for over decades. And what's weird in that map is you see that weird circle at the mouth of the bay. That's actually where a meteor hit the mouth of the bay like 30 to 40 million years ago. So that's why there's that weird circle. But bottom line is because this aquifer does not get naturally replenished, it has declined by over 200 feet in the last 100 years. Actually, there's no new industrial permits allowed for withdrawals out of the aquifer. And hopefully with SWIFT, we could recharge the aquifer and they can open that up again. But what's also happening with the groundwater withdrawals, and if you look at the graphic on the right, you look at those contours, those contours represent the rates of sinking of land subsidence. And so, and it's happening not just around where those paper mills are, but it's happening all across Eastern Virginia. And the OECD ranks Hampton Roads as 10th in the world for value of assets at risk from sea level rise. So sea levels rising, Eastern Virginia is sinking. And so the idea is, and we've got data that suggests that if we can pump water back into the aquifer, we can either slow or stop the land subsidence component. So 50% of observed sea level rise is attributed to land subsidence. About half of that is due to over withdrawal of the aquifer. And if you haven't heard, Jakarta is the fastest sinking city in the world. They're primarily sinking fast because of all of the wells. They're pulling all of that water out of the groundwater and it's causing them to sink. And they're an island, they're right next to the ocean. And so now they're experiencing a significant amount of sea level rise, and they're actually looking to move their capital city inland. So this is a quick update on SWIFT. We're looking to put 50 million gallons a day of SWIFT water by 2029 with 2 plants. The first plant will come online in 2026. The second plant will come online in 2029. And so with that, I'm going to turn this over to Dr. Bott.
So, Jay, are you sure you don't want to do a few more slides there? Is this? Oh, you're muted. Okay.
You can do that.
I can. Okay.
What is this, hot potato? Which one of you
Yeah,
gets
I
to-
got it.
Yeah.
I got it. There we go.
Sorry about that.
Two there. Okay, hopefully that worked. Can you see my screen okay? Okay.
Yep.
Okay, thank you. So I'm going to tell you a little bit about HRSD's R&D department, a little bit about what we're doing. These pictures are some of the technologies. We're going to go through more of that. So, and I apologize for the noise if you can hear it. It's raining like crazy outside here. So the Water Technology and Research Department at HRSD, there are actually 2 of us, myself and Chris Wilson, who run this. We have some treatment process engineers, most of whom now have come out of this program over the years, have gone off to work for various engineering firms and other entities and have come back to work for us. We typically have about 15 graduate students working at our facilities through various university partnerships. It's about 1/3 PhD students. or so, and 2/3 master's students, roughly. We're participating in a number of Water Research Foundation projects, and we've done grants funded by DOE and EPA over the years. The drivers for us are process intensification and decarbonization, quite frankly. We've got, being at the mouth of Chesapeake Bay, regulations are driving us to lower and lower levels of nutrients, and will effectively be at a load equivalent of 4 milligram per liter TN by 2026 and 0.3 TP by 2032. Jay talked about SWIFT, and that places even more stringent demands on nutrient removal. So speaking of SWIFT, I'll talk about some of our interests. So first of all, SWIFT is really based on CBAT, or carbon-based advanced treatment. No membranes, and one very important part of this from an advanced treatment standpoint is that it requires a really good wastewater plant upstream doing really good nitrogen removal in particular. And that, of course, brings some other benefits in terms of emerging contaminants. So a lot of our R&D is focused on SWIFT, and this slide calls out both the process flow diagram and some of the research interests and some of the things we're working on. For example, ozone maximizing emerging contaminant removal, disinfection, and minimizing bromate and other disinfection byproduct formation, biofiltration. We've done a lot of work on co-metabolic 1,4-dioxane removal with propane addition, and this is actually operating full scale now at the research center, and is in design for the second full scale facility. We've also done a lot of work on removal of those emerging contaminants and disinfection byproducts through biofiltration. A very important topic for us right now is minimizing GAC usage for PFAS removal. We have a number of projects, so minimize the amount of GAC that we use, or make the reactivation of that GAC more effective and more reliably mineralizing those PFAS compounds. We've a lot of work now going on recharge well design and operation. We've learned a lot about what not to do with recharge wells, and we're working hard to figure out what are the appropriate design and operational criteria for these recharge wells, which are a really big investment in managed aquifer recharge. We also have done work on pre-treating leachate as a means of better managing compounds, including both PFAS and 1,4-dioxane. So building on a successful pilot, now full-scale biological treatment of 1,4-dioxane at a landfill. This is a waste management landfill using tetrahydrofuran as a co-substrate. So a few years ago, we partnered with Waste Management to implement that. Then effectively removes all of the 1,4-dioxane from this landfill leachate in their existing biological treatment system, which was a really cost-effective solution for us and for Waste Management. So building on that, we're now moving into specifically going after PFAS. That includes pilots of foam fractionation, which really, a foam fractionation pilot was not necessary. Lab testing was sufficient to confirm that foam fractionation would be effective on the pre-treated leachate, the biologically pre-treated leachate. So really, foam fractionation was not necessary. But foam fractionation pilot work is necessary to generate the foamate, the concentrate, for pilot testing of the destruction technologies that will be tested at the landfill this year. And you see the list of technologies that we will be piloting in collaboration with Waste Management. And Jefferson Lab will be doing work with E-beam that we've already worked with them to test for 1,4-dioxane removal as part of that as well. And then that project will move to implementation with at least foam fractionation, and subject to the outcome of this pilot testing, perhaps a destruction technology for the concentrate as well. So with that in mind, what I really would like to do now is take a bit of a deep dive into some of our work in the wastewater space. So I mentioned already that nitrogen removal in the wastewater plant is an absolutely fundamental and critical part of making CBAT work, and it's a critical part of what we need for compliance with the Chesapeake Bay program. And we've spent a pile of money on the capital and now on the operational costs associated with doing nitrogen removal. you know, the conventional nitrogen removal is what we know how to do. And since we're taking a deep dive, I want to make sure everybody is clear on what we're talking about here. So when we do conventional nitrogen removal under aerobic conditions, we oxidize ammonia to nitrate in 2 steps with ammonia oxidizing bacteria and nitrite oxidizing bacteria, although now we know about common existing that can make this oxidation in 1 step, 1 single organism. Then we do denitrification of nitrate back to nitrogen gas. And, you know, we know how to do this. And for Swift, even and for meeting the low level requirements we need in the Chesapeake Bay, we know how to do this. But it's not hard. Sorry, it's not easy. I mean, it's really challenging and it's really expensive. And it's already reliant on sensors and sensor-based control systems to make this as cost-effective as possible. So this is an example of our Nansman plant. It's a 5-stage Bardenpho plant, and we for many years have been running feedback ammonia-based aeration control, where we have ammonia sensors at the end of each of these aerobic zones that are used with PID control loops to control DO set points upstream. We also have nitrate sensors at the end of the first anoxic zone that's being used to control the amount of internal recycle pumping from this location at the end of the aerobic zone to the beginning of the first anoxic zone. And then last, we have nitrate sensors at the beginning and the end of the second anoxic zone that are used with feed forward, which is just the feed forward part is just stoichiometry, and a feedback PID loop to control methanol feed. So all of that is sort of in place, operating basically at all of our plants and necessary to do conventional nitrogen removal in a cost-effective way. And so really the objective is to go beyond that. And going beyond that is, I'm sure most of are familiar, is really shortcut nitrogen removal. And the big, you know, the reason that we draw this triangle here is because it becomes obvious that if we can figure out how to grow AOB and not NOB, we get a benefit of shortcut nitrogen removal, and this would be called nitrite shunt. It turns out that this is really hard to do in the mainstream part of a treatment plant. It's quite easy to do in the side stream and warm water that's very high in ammonia. We know how to do this, but in the main treatment plant, it's really a challenge. And then if we take that 1 step further and start talking about Anammox, an organism that grows quite slowly but uses ammonia as its electron donor and nitrite as its electron acceptor, going straight to nitrogen gas, well, then we end up with a process that's now known as deammonification or partial nitritation, Anammox PNA. This is, of course, the goal. This is where we want to go. And there are 2 big challenges: retaining Anammox and out-selecting NOB. Number 1, I think we've pretty well figured out. We know how to grow Anammox. They're tough. They grow slowly. We need to accommodate their slow growth rate, but we know how to do that. It's the NOB out selection part that's hard, except in side stream. And so we've been doing this in side stream. We installed Demon at our York River plant in 2012. This was the first side stream deammonification process in North America. And this little tank here, that little baby tank there, treats about 20% of the nitrogen load on this plant effectively for free. And so, yeah, doing PNA on the side stream is just a no-brainer now. We did it with a different process called a Nitamox at our James River treatment plant. We're installing another one at another treatment plant and starting that up this year. So side stream is no problem. It's mature now. It's not plug and play, but it's certainly mature. But mainstream, you know, there have been a lot of work over the last 10 or 15 years, but really pretty limited reports. And I would argue that none of these plants are really removing a significant amount of nitrogen through the Anammox pathway in the current time. And this plant in China maybe is a little uncertain exactly what's going on there. But really the challenge here is out selecting NOB, and that limits the implementation of mainstream PNA. And so while we can't do this, while we can't do mainstream PNA, what we can do is mainstream pDNA, partial denitrification. So instead of feeding nitrite to Anammox by shortcutting the nitrification pathway, we do it by shortcutting the denitrification pathway. This has been called pDNA now, and the detour to get to a shortcut is attributed to Heidi DeClippier at DC Water. This is a detour to get to a shortcut, and you know we continue to use this word detour to describe this. So at HRSD, we set up a pilot facility back in 2012 and really that was focused, quite frankly, on mainstream P&A at the time. And we didn't get serious about mainstream PD&A until around 2014, 2015, and things really started clicking. We went full scale immediately from there in 2018 at our York River plant. I'll talk about that a little bit. This is that original pilot facility and the original MBBR where we did a lot of the this PD&A work to start with. All of this was done in collaboration with DC Water, and these are some of the teams of graduate students from a number of universities, but primarily Old Dominion University and Virginia Tech, that moved through that pilot facility over those years. And we finally got there. So this is being commercialized under the name Detour. And we're now doing this full scale. We're also still doing pilot work. So the original pilot work in 2012 to 2018, we ran a filter pilot at York River 2020 to 21, but that was after the full scale work. And then James River, we're continuing to do MBBR and IFAS related work there. This is a picture of the pilot facility that we have there and some of the graduate students who have worked at that facility. I need an updated picture. So from a full-scale status, so I mentioned that we did PD&A and post-D-night filters that were existing at York River in 2018. It took about a year to get to a stable place, but that's worth for 13 MGD plant operating at 13, about $1 million per year in chemical and energy savings, and we completely eliminated a big project to upgrade that plant for more sustainable, conventional nitrogen removal. I'll say we just decided we didn't need that project at all. And that was because of getting anammox growing in the filters. We've now upgraded James River plant, and I'll talk about that. That's IFAS in the second anoxic zone. We've established that full scale. That was a big deal because we actually designed and built a capital project and then established anammox. We were all very proud of that. This was not an existing facility like York River. And then Nansemond is our second one with a startup of the first tank in January of this year. We have a polishing MBBR at Nansemond under construction in 2025 that will be starting up later this year. And we still have our side stream P&A processes operating at all the plants where we need them. So while we would like to have P&A, and while we would like to have anammox doing all the nitrogen removal at a treatment plant, this is what we know how to do right now. And this is inherently then most applicable for plants with pretty stringent total nitrogen requirements. So post-anoxic zone type things. And again, there are lots of other research topics. This is what we know how to do. So the York River example of doing it in a D-night filter or in a polishing MBBR, which is also happening at the Noman coal plant and one of the Fairfax County wastewater plant, and the second anoxic zone in an IFAS type application. Regardless, it turns out that the really challenging part is not growing anammox and is not achieving partial denitrification. The challenging part is feeding the process properly with control approaches like AVN, where we have to match the ammonia and NOx ratio in order to provide anammox what it needs in order to get to low effluent TN. And we do that AVN control by manipulating DO, aeration time, step feeding, et cetera. So one thing that is super, super important about this, though, in fact, really there are, of course, methanol and supplemental carbon benefits, and there are energy benefits, and there are probably opportunities to improve BioP by doing this and minimize alkalinity addition. So there are all kinds of chemical and energy benefits and decarbonization benefits. But the big one for us from a cost standpoint is the intensification benefit. Under normal conditions, we design aeration tanks and secondary clarifiers for a wintertime condition where we need to get the ammonia concentration to a low value here or here. And we no longer need to do that. Because we have anammox in this downstream anoxic zone or in a filter, we can rely on that process to remove ammonia to the low levels we need under anoxic conditions. And that completely changes the paradigm for how we size the aeration tanks and clarifiers. And so it turns out that PD&A is a very important intensification process as well. So when we say intensification, what do we mean? Well, of course, I mentioned we need to minimize the resource inputs we need. But from a cost standpoint, from a capital cost standpoint, it's the concrete tank size, the capacity of those concrete tanks that's super important. Getting that capacity, improving BNR and existing aeration tanks and clarifiers. And you know, this is my interpretation, but there are several ways to get that intensification done. One is to manage mixed liquor settling limitations, the granular sludge, indents, Narita, MBR, where we don't even need to settle those solids. We separate them with a membrane, selectively retaining slow-growing nitrifiers and therefore decreasing the aerobic SRT and can decrease aeration tank size, and there are lots of options there. But one very valuable one that's quite relevant for plants with stringent nitrogen limits now is moving the ammonia removal out of the aerobic zone, and PDNA and maybe MABR give opportunities to do that. So back to James River plant. At James River plant, we were able to carve out a very small second anoxic zone, and it can be small because it's IFAS anyway, because of the need to grow anammox. We put plastic media in this zone. We added screens on the influent and effluent side. We have only 15 minutes, and we started this up, and exactly as predicted by the pilot work that we've done over and over, it took about 3 months with virgin plastic media here, about 3 months with 1 milligram of ammonia and 1 milligram of nitrite around to see our first anammox activity, and about a year to get to full anammox capacity. So that's pretty exciting, and we have now this in place in all of the tanks at the plant, and this summer is very definitely anammox growing season for us at this plant, and because next year will be when we're facing more stringent nitrogen requirements. We've extended this to Nansman plant. We started up one of the 6 tanks here in January 2025, and what I mean by that is that we've taken the first cell of the existing second anoxic zone in these tanks, and we're building 2 additional tanks associated with a plant expansion. The first cell will be IFAS or is IFAS, and then the second 2 cells are full denitrification nitrate polishing. We started up one of those tanks. We realized we made some errors in how these tanks are configured, and some design issues. And so we got that tank out of service. We're making some changes, and we'll be doing that and putting it back in service in the next couple of months. This project and the James River plant are actually part of a DOE grant that AECOM is leading on PDNA right now. Another of our technologies that we developed actually also with work at James River plant was done quite a long time ago now is indents. This is continuous flow densification using cyclones, and is now been delivered at more than 100 plants active, and a couple of these are expected projects. So this is really moving quite quickly, and we're proud of this. And we are now in HRSD extending this to memdents, which is the application of indents in membrane bioreactor plants. Some of our small plants are membrane bioreactor plants. One of the things that we're also excited about and really have no choice in is as we operate more and more plants in ammonia-based aeration control and in AVN control, low DO is no longer really an option. It's sort of a fact. We're headed there whether we like it or not, and we really need to understand it better. And so we took our BNR pilot facility, we actually moved it to a different treatment plant. We have a new team of students, actually several groups of students have been through this facility as well, and now focused on understanding the acclimation of autotrophs and heterotrophs to low DO. And this is also a big emphasis now on biological phosphorus removal. So thinking about ABAC and AVN control, this is also something that we need to improve as we think about PDNA. So most of our plants operate in feedback ammonia-based aeration control, an ammonia sensor here with a PID loop that's controlling DO set points upstream. This is typically feedback only, PI control, and it works, but it's not perfect, and it's most cases not sufficient for PDNA if we want to go to low concentrations. So we set about a program to improve this, and the improvement of that PDNA is really focused on improving AVN control. So now it's an ammonia divided by the ammonia concentration divided by the NOx concentration. So 2 sets of sensors here. And there needs to be some feed forward part of this. And there are several ways this is being done. One is a controller that adjusts for changes in influent flow. This is already applied to AVN. Mike Parsons set this up at James River, one of our pretreatment process engineers. And while it sounds quite simple, it's actually pretty hard to program because that model is basically knowledge of what should be the DO set point based on the influent flow. What makes this easy is that that plant is already aerobic IFAS, and it's a lot easier to predict what the DO needs to be for a given flow rate or a given condition. Ali Gagnon, who's also a PhD student at Virginia Tech and a treatment process engineer at 2 of our treatment plants, has worked on a really cool feed-forward model predictive controller where she did regression analysis of a whole lot of process simulations of a calibrated process simulation model using Sumo, which is the modeling tool that we generally use for all of our process modeling, and no additional sensors. And then Jeff Sparks' work, which is a combined hybrid mechanistic model, which is again is a Sumo model running as a real-time digital twin on the plant control system, combined with a data machine learning model and an added ammonia sensor here. That is the feed forward part, and it continues to be backed up by a PI loop for the feedback part. And that's running in ABAC and very soon AVN as we establish more and more Animox at our Nansemond plant. So, one of the other things that this requires is good sensors. And good sensors is something that we've struggled a lot with, and we've really worked to think more about. And we set up a program a few years ago with 2 pretty special guys. One guy named Josh Walker and another Arba Williamson. Josh has now been replaced with Shelby. But the term jarbalizer came from Josh and Arba, and this is our own HRSD designed and fabricated. We build these. These are colorimetric analyzers, do ammonia, nitrate, nitrite, and orthophosphate. We can do a lot of other things though as well. We built about 20 of these, and we're using quite a lot of these now at our full-scale treatment plants. And it's taken about 8 years to get this going, and there's some pretty innovative things built into this analyzer system that we're now working to commercialize. So this is the sort of final product here at one of our treatment plants. Another of our products is on the complete opposite end of that spectrum. This is a very super simple mixing system. That's basically an inverted siphon using air from the low pressure air system at the plant. This is known as a minion mixer now because the guys at a treatment plant dressed one up like a minion, and that name stuck. And we have these operating at 6 of our treatment plants. We've now commercialized this as well. Very low capex. It's basically PVC fittings, uses low pressure air, basically no maintenance, and it's extremely low energy compared to mechanical mixing. But we don't claim that because most of our blowers are oversized anyway, and we waste a lot of energy wasting air into tanks, offline tanks anyway. So, but yeah, very low energy as well. So what's next for us? Well, PDNA is very important for us. We're going to continue to develop and deploy that. PNA is really our future goal, and we have research starting with the hypothesis that pDNA is really the path to PNA, and I can talk more about that, but we have a lot of work getting ready to get started in that area right now. We always want to use wastewater carbon as efficiently as possible, and that nitrate-based internal recycle control is an important part of that. Low DO, we're headed there whether we like it or not, and it just makes sense, and it probably, if we're interested in doing good biological phosphorus removal, and that's what we are, making BioP truly reliable even in the summer, it might be that low DO is the pathway to get us there. I know I didn't talk about BioP here, but we have a whole program on this as well. Sensors and controls is a big part of our work, digital twins, AI and ML, incorporating that right into plant control systems. But we don't forget about optimizing and designing well our PID loops. We're still reliant on PID loops. We will continue to be reliant on PID loops, and we like to make sure that we do that well. We've just hired a new director of digital water. It's the same guy that I mentioned, the Jeff Sparks, that developed that really cool ABAC controller. And he has about a dozen projects that are really cool that hopefully solve some interesting problems for us as well. So what have we learned? Applied R&D managed the risk of deploying new technology. We didn't really have to wait to do DEMON. We were already working on mainstream P&A from an R&D standpoint. We didn't need to wait to do sidestream P&A if we really were, working on mainstream P&A. Don't wait for others to bring innovations. Be the catalyst, not the client. That's kind of our motto, I guess. We remain relevant. We must remain relevant to our installed base of aeration tanks and clarifiers. We have mostly brownfield plants. We're not building new treatment plants. We've got a lot of aeration tanks and clarifiers that we need to use effectively. Our utility partners are not competitors, so we try as much as we can to collaborate, and we get universities, consultants, and technology providers involved, but we really need to drive our goals, and our team really is the most important part. So I'll turn back over to Jay here.
Thanks, Dr. Bott. And hopefully you can see through some of those pictures how elaborate some of our pilot setups are. And again, I think that that's what's unique about us in terms of our ability to pilot technologies at scale. And as Dr. Bott said, when we innovate, it's demand-side innovation where we are trying to solve a problem that exists. But yeah, so we would love to build partnerships and collaborations. So please reach out to us. Our contact information was at the front, and we can send that to y'all. But with that, Peter, we're ready to take any questions.
Great, you guys. Thank you so much. And you're right. It changed a lot since the last time I heard this talk. So that's great. And Charles, thank you so much for going in so deep. So I know everybody is to remind you, the chat window is your angle, your avenue for asking questions of our guest today. And I'm going to get to those in a second, but I want to ask you just one question first, Charles, because you alluded to it at the end. What do you think the most kind of interesting frontiers of new technology, new innovation are outside water treatment that you think are going to inform water treatment? You kind of mentioned AI and ML as obvious things that are frontiers of research that are moving very rapidly. Are there any other things, sort of other research areas that you think hold particular promise for the sort of work that you guys do at Hampton Roads?
Yeah, I mean, sensors is obviously a really big deal for us. Having good sensors that we can rely on, that then enable more sophisticated, more appropriate control systems. That's a big deal. One of the biggest challenges we've had is taking our existing SCADA distributed control systems, PLC systems, and the actual approach of integrating the AI ML into those systems is not trivial, right?
Yeah.
So we buy these products. That's a real challenge. Yeah. So we've figured out how to do it just by brute force in some ways. But yeah, I'll just offer that.
One thing I was in your talk, you didn't mention much of anything about genomics, metabolomics, and kind of other kind of biological tools for optimizing those systems. Is that because it doesn't really play much in your space, or is it something that you do? We just didn't talk about it today.
So we achieve that. Well, first of all, I'm going to answer this question in two parts.
Yeah.
Number one, we have a really capable lab within HRSD. We call it our pathogen lab. We're capable of a lot of molecular analysis, and we did wastewater surveillance work way early when in COVID. And that we had that capability because we already had that group that was doing pathogen monitoring. That was for surface water monitoring of pathogen indicators and pathogen markers by molecular tools. and then pivoted really easily over to SWIFT, monitoring pathogens at very, very low concentrations for SWIFT advanced treatment. And we've done a lot of that work. From a process standpoint, from a wastewater process standpoint, thinking about COMAMOX and ANAMOX and AOB and NOB and PAO and GAO, that's what these icons are all here. So Kartik Chandran at Columbia, George Wells at Northwestern, April Gu at Cornell, Amit Pinto at Georgia Tech, Amy Pruden at Virginia Tech, Nancy Love and Lute Raskin at University of Michigan. That's what a lot of what we go for university partnerships is the molecular work, process molecular work that we do some of ourselves, but we don't do everything we need ourselves for that. Yeah, so that's an important part of everything we do, and that's an important part of our university collaboration.
Great, great. I see Zipporah Wagner had a question here. Zipporah, why don't you unmute yourself and ask your question directly?
Thanks so much, Peter. Thanks so much to the presenters. Can you guys hear me?
Yeah.
Great. So I'm really curious about, how you maintain a sort of sustainable innovation ecosystem. And one of the things that comes to mind is if you have a lot of pilots, a lot of full-scale deployments, that you're going to, inevitably have some failures and like clutter. And I'm wondering if you have a decommissioning or a takedown process to, try to keep space open for new things coming in.
Yeah, definitely. So right now we have effectively 4 pilot facilities, one focused on the low DO work, one focused on our PDNA work. One is our SWIFT Research Center, which is where all of our advanced treatment work is going on, and one focused on anaerobic digestion work. We have most of those pilots have been through many different versions, right? So we're continuously learning how to pilot differently and better and pilot new things, and we simply just take it apart and rebuild it to address the question that we want to learn. So from a pilot standpoint, it's easy, right? We have the capability to design and build pilots, and we're, our main BNR pilot is on version 15 probably of things we've done over the years, and we've learned a lot about what not to do. But you're right, things we get into a pilot and we realize, oh, this is just not going to work, and we have to stop and redo and start over. And that's part of it. And I work hard to make sure that Jay is aware that those failures in pilots happen, and our commission as well, and that's why we do pilots. And we all say that SWIFT Research Center, the 1MGD facility, and the smaller pilots that go with it, we all say to ourselves all the time, thank goodness we built that facility before we scaled up, because we learned a ton. But full scale developments fail too, and we have had pilots that were just a complete failure from the beginning. Years ago, we did a pilot where the objective was to try to ferment grease and primary sludge together. And we had all kinds of what I thought were great ideas for how to do that. And that pilot was a stinky mess, and we just never got anywhere with it. And finally, we just said, okay, this one just didn't work. We've got to pull the plug on this. We're not going to spend any more money on it. We didn't spend that much money in the begin with, but we had to pull the plug. Full scale is harder, right? And we try really hard when that happens to fail fast, make changes, and move. And we just had a pretty substantial one at our Nansemond plant associated with starting up the first PDNA tank. And I think it's important that people talk about this. If I had time, I would. I think it's important to talk about these failures. So in this case, it's kind of a complicated story, but the first tank we started up with the plastic media, we had the influence screens retaining that media in that tank plugged up with rags that should have been removed and were not, and that's all been fixed. But it caused excessive head loss that then moved into the actual tank itself. A high water level, media backflowed. It got transferred around the plant with some pumps, and it was a mess. We luckily didn't lose much, if at all, of that to the receiving stream, but it was a mess to clean up. It took about 2 weeks to do it, and but we've already got a design improvement, a design for an improvement in place. The contractor's willing to work with us. We've got a young process engineer who's absolutely fanatical about getting ANAMOX going in this plant, and that helps. And she is all over designing an appropriate modification to make sure that doesn't happen again. And we've fixed all the screening now. So, so yeah, hopefully we're good to go in the future. But I think the important part of that is it's constant work to keep something moving like that after such a big failure. And it's also important to fail fast, even at that scale. Fail fast, immediately start working on improvements for the design and get those in place. So we're gonna have a change order to pay. Hopefully it's not too big, but we're gonna have a change order at the end of all of this. So,
yeah. Well, guys,
Thanks so
I
much,
want to
Charles.
wrap up. Thank you very much for that question, Zipporah. I want to wrap up and maybe talk more, I won't call it philosophically, but Charles, you mentioned a little bit about the role that some of the academic partners play. They have special capabilities, and that's one of the ways in which they differentiate and make a role. And, you know, we at NAWI think a lot about how these, you know, various constituents, water utilities, academic and research partners, industry partners, what they bring to the table, what roles they play, et cetera. So let me kind of wrap up and not to be too cheeky, but you know, we sit at the intersection with academia. We have a number of young scientists on this call, et cetera. Charles, what do you wish PhD programs did differently? And are there any quote unquote bad habits that you wish would be addressed in the PhD program?
We're open. We're open to collaborating with anybody and everybody. And I do get a lot of calls from young faculty members at universities wanting to work with us. And I often say, well, what do you have to offer? And because we're open, let's find a project that we can collaborate on, and let us find a way to help fund that student and get them to one of our facilities to work on what, you know, we collectively would like to work on. That's how we operate. I'm not sure I have suggestions for improvements, but that's how we like to do things. So we're super receptive to that collaboration. And I'll just say that it's really often about, while we do have a lot of collaboration with Virginia Tech and ODU because they're local in-state universities, and because we have good collaborative relationships there and have for a long time, we do work with a whole lot of other professors and faculty members at a wide range of universities, but it's based on that person, right? It's typically based on that faculty member that knows how to work with us, that brings something that we need. And yeah, so that's our mode of operation. But I think it's really helpful if a utility steps forward and says, we will host a graduate student, but also give them the time and the space to do the research that they need to do to get their degree. So it's one thing to have them come and help operate a pilot, right? That's not the hard part. The hard part is making sure they also have the time and the space to do the work they need to do to get the papers and produce the work that is of an appropriate quality to do that. And it takes some trust, establishment of trust that we or any other utility is going to do that, right? That's the hard part.
Yeah, good. Jay, any other final words?
No, thanks. Just really, thanks for the opportunity to help us tell our story to a different group of folks. So we really appreciate the time.
No, we appreciate you guys so much, and everybody on the behalf of NAWI and our community. We look forward to many exciting discoveries ahead coming out of Hampton Roads, and from all of us at NAWI. Thank you guys very much for your work, for your openness and your collaboration, and everybody in the NAWI community. Stay tuned for future great content on our webinar series. And from all of us at NAWI, thank you so much for your attendance today. And the recording will be available on the NAWI website. Charles and Jay, thank you so much. Enjoy that rain, Charles. We don't get much of that in California.
It's unusual here.
Yeah.
Crazy.
All right, everybody. Have a great day.
All right, take care.
Bye-bye.